Now, Isaac Newton is one of the two people that are credited with inventing and discovering calculus. So, what was Isaac Newton up to? What he wanted was a mathematical way to deal with physics, because that's what he was doing. He was working on the laws of mechanics, right? Newtonian mechanics. So, objects in motion tend to stay in motion, objects at rest tend to stay at rest. Objects moving in a direction will stay going in that direction unless they're acted upon by another force, and also gravity and that kind of stuff. So that means that we have to deal with a lot of physics applications in a calculus class because they were developed hand in hand together. And it allows us to do science problems that we were never able to do before. So we're going to continue in that vein in this section. We're going to do a lot of different physics applications. Number one topic is density and mass. Now, you probably learned a long time ago in some science class that mass is density times volume. And that's true, but it's a little bit of a cheat because it's predicated on an assumption that the density of the object is uniform. But density is not uniform, not when we have calculus. So with calculus, we can let the density vary and still be able to do this. Now, this is something we were not able to do before calculus, right? So when you're in your basic science class, they just tell you this basic formula, but now we know we can go a step further. All right, so let's think about a thin object like a wire. And I have it's sort of a wire drawn. It's a rectangle, I know, but you have to pretend that it's very, very thin, infinitesimally thin, and pretend it's just a wire. Okay, so if this is a wire, you can see that over here it's less dense because it's lighter. And over here it's more dense, it's darker, it's more packed in. Right? Density is how much stuff you're packing into a region. In this case, it'll be a one-dimensional line. So how much stuff we're packing into a line. Now, we imagine that we have density, and what we're going to do is we're going to break up this wire into infinitely many pieces, which means each of them will be infinitesimally thin and small. And you can tell what we're about to do, right? We're going to add them up, right? So if we add up infinitesimals, that means we're integrating. And that will give us the mass of the object, which leads us to this formula down here. So if we have a thin wire. Now notice this is only for one dimensional. That's why it's talking about a thin bar or a wire, because we're only talking about one dimensional mass at this point. There are ways to find two-dimensional and three-dimensional mass. That'll involve Calc 3 and more variables. So we'll deal with that when you get onto that class. All right, so we have that bar. It's represented by the interval a, which is less than or equal to x, which is less than or equal to b, because of course it only has one dimension. So you're just going to let it be from a to b. It has a density function. Now I know that looks like a p, but that's rho. Rho is the density function. Rho, it's a Greek letter. Right. Now rho is going to be measured with some units of mass per length. We'll talk about that when we talk about units down below. And that will get us the mass. So the mass is equal to the integral, because of course we're going to add up the different density pieces. So this is the linear density. Function, right? Because it's changing. It's not going to be constant. Well, I mean, if it was constant, you just put in whatever constant value it was. But if it changes, this works. And then, of course, dx, because we're going to have a tiny delta x distance in the wire. And then, of course, we're going to add them up, right? So, and when we add up infinitesimals, when they're infinitesimally thin, then that means that we're taking an integral. It's amazing how important those fundamental theorems are from Calc 1 for this. So that adding up infinitesimals, we've used it all over this chapter. All right, now the density function would have linear density units. So linear density would be things that are like units of length, or excuse me, units of mass divided by units of length, right? So for example, grams per centimeters or kilograms per meter, that kind of thing. Now, the last bit before we go on to the next page is that the rho of x and the dx must have compatible units. So let me give you an example of that. So rho of x gets multiplied by dx, right? So I have to have it be length here, and I have to have it be mass divided by length here. So when they say compatible units, what they mean is that the lengths have to be the same kind. So let me give you an example. Suppose I had grams per centimeters for rho of x. I would need to multiply it by centimeters. Or if I had kilograms per meter, then I better be multiplying by meters for my length unit. All right, now let's actually put this into action with an example. If I can grab my paper. All right, we have a thin 4-meter bar made of differing alloys such that its density is 5e to the negative 2x kilograms per meters. What is the total mass of the bar? Interesting. Let's take a second and look at what 5e to the negative 2x looks like. So it looks like this. And you can see that it's larger, value of 5, when x is 0. And as we move towards x is 4, it gets smaller and smaller. So what that means for our bar is, of course, it's going to start off with a lot of density. It's going to be very dense over on one side. So let's pretend this is x equals 0, this is x equals 4. And over here on this side, it's going to be very, 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 very dense. And it's going to get less and less and less and less dense as we move along. So over here, it's super packed in, and then kind of medium packed in, and then just a little bit, right? So over here, it's very dense. And over here, it's not dense. Okay. All right. So then we should be able to find the mass. So the total mass, which is m, is the integral from a to b of rho of x dx. All right, well, I know the density function because they gave it to me. Rho of x is equal to 5e to the negative 2x. I obviously know I'm working with respect to x. That's no problem. Now, where did the 0 and the 4 come from, you might be asking? Well, they say it's a 4-meter bar. So why wouldn't you establish 0 and 4 as your interval? And sure enough, you would. So I would take the integral from 0 to 4 of 5e to the negative 2x. All right, well, that's going to involve u substitution. So u is equal to negative 2x. du is equal to negative 2 dx, which I obviously do not want. I really want negative 1/2 du. And then since I'm going to be using a definite integral, you definitely want to show all this work, right? So x equals 0 means that u is equal to negative 2 times 0, which is 0. And then when x is equal to 4, u is equal to negative 2 times 4, which is negative 8. Wonderful. All right, so then I can rewrite this integral and say I'm going to go from 0 to negative 8. There was a 5 and then a negative 1/2. Oh, I actually should put those in front. Hold on. There we go. So we have a 5 here, and then we're going to have a negative 1/2 from the constant. And then it's e to the u du. All right, well, that was all well and good. So now let's actually integrate this. So this is negative 5 halves. The integral of e to the u is e to the u, so that's easy. But then we're going to take it from 0 to negative 8. So this is negative 5 halves times e to the negative 8 minus e to the 0. Now, e to the 0 is not 0. Don't forget, e to the 0 is 1. So this is negative 5 halves 1 over e to the 8th minus 1, which, who wants to know what that is? I mean, that's ridiculous. So we will go to Desmos and make Desmos tell us what that value is. There you go. It's 2.499. Now you'll notice that on Desmos, I'm not able to use row. Well, I guess I could have. I didn't even check. I just called it R of X because I figured it was easier. So it's 2.499. Now it's 2.499 what? So if we go back to the problem, we can see that rho of X was given in kilograms per meter. So this is in kilograms per meter, which means dx has to be in meters. So when we add up the stacks, we're getting rid of the meters, and that'll leave us with nothing but kilograms. So this is 2.499 kilograms.